1.9 Prime numbers and prime factorizations. Okay, understand the difference between prime and composite numbers. Determine whether a number is prime or composite. Find the prime factorization of a composite number. And find all the factors of a composite number. Okay, first off, what is a prime number? Okay, a prime number is a counting number greater than 1 that has exactly two different factors or divisors. Okay, itself and 1. What it's saying is, and I'll go ahead and give you an example of one. Okay, like say 2. Well, how can I ever make 2? Is there anything that I can multiply together or factors that could ever create 2? Well, I can think of 1, and that's going to be 1 times 2. Well, and that creates 2. But I can't think of anything else. Okay, so that right there is the definition of a prime number shown. So there's one example of a prime. Okay, now a composite number. A composite number is a counting number with more than two different factors. Okay, once again, let's kind of go again. Let's use, like, say 4. Well, 4, let's think of factors of 4. Well, just like the last one, I know that I can multiply 1 times 4 and I get 4. But notice automatically I can also do 2 times 2 and that equals 4. So notice I was able to get, now here I was just able to get 2, but that is still more than just 1. And so therefore I have a composite number now. Continue on. Okay, talking about 1. Okay, notice you can say 1 times 1 is you would probably think it's a prime number, but hold on. Okay, 1 equals 1 times 1, and 1 is the only factor of 1. 1 does not have exactly two different factors, okay? And it does not have more than two different factors. Thus, 1 is neither a prime nor a composite, okay? So when we start doing prime numbers, we start at 2, okay? If you start with composite numbers, you would start at 4. So continue on. Notice here, just use an example that they give us. Example 1, determining prime numbers. Okay, the following numbers are prime because each has exactly two different factors, 1 and itself being whatever number that you've chosen. Okay, 2 has exactly two different factors, 1 and 2, because 1 times 2 equals 2. Okay, 7 has exactly two different factors, 1 and 7. 11, same thing, 1 and 11. And 29. Okay, 1 and 29. And there are infinitely many, okay, prime numbers. Okay, so composites, let's look at them. The following numbers are composite because notice 1 and 12. Well, I've got 12, so 2 times 6, that equals 12. 3 times 4, that equals 12. So 1, 2, 3, 4, 6, and 12 are all factors of 12, and 12 has more than two different factors. So therefore, it's composite. Okay, let's look at 33. 1 times 33 equals 33. And 33 times 11 equals 33. So 1, 3, and 11, and 33 are all factors of 33. And 33 has more than two factors. So that's how we would know it's composite. Okay, to determine whether a number is prime, divide the number by progressively larger prime numbers, 2, 3, 5, 7, 11, and so forth, until one of the following is true. 1, the remainder is 0. Okay, once again, you notice by then, that means it's divisible. This means that the prime number is a factor and the given number is a composite. You find a quotient smaller than the prime divisor. This means that the given number is prime because it has no smaller prime factors. Okay. Determining whether a number is prime. We divide only by prime numbers. That is, there is no need to divide by a composite number. The reasoning is that if a composite number was a factor, then one of its prime factors would have to be found in an earlier division. Okay. Let's look at one. Let's do, is 605 a prime number? Well, let's think back. Thinking back to our divisibility, notice that in my ones place, there's a 5. Okay, so in the ones digit, therefore, it's going to be divisible by 5. Okay, and so therefore, it's not going to be a prime. Okay, it's going to be composite because that means I could multiply something by 5 to get to 605 eventually. Okay, so let's look here. We've got 605. If I decide to write that out, I could do 5 times 121. And if you remember, it's saying that I could split one of these up to where there's actual primes. So I got 5 times 11 times 11. Because 11 times 11 gives me 121. Multiply that by 5, and I'm going to get my 605. And so I know that the factors of this are going to be 5, 11, 121. And if you want to get serious about it, you could actually put down 1 and 605. Okay? Because remember, we do have the 1 times 605 in there. Let's look at the next one. 103. Is 103 a prime number? Okay? Well, looking at it closely, we can start doing the test for 2, 3, and 5. We notice that the 2 is going to fail. Okay? Because 1, that's not an even number in the 1's plot space. 3, we could try that out, but look, 1 plus 3 is going to be 4, so that fails. And then also 5. 5 is going to fail. So the number 103 is going to end up being possibly prime. We can still do some more checks though, okay? So let's start checking by greater prime numbers. We notice that 2, 3, and 5 don't work, so let's do the 103 and let's divide it by 7. Because 7's a prime. So 7 will go into 10 one time, leaving me with 7. And then we can come in here and go, that's going to be a 3. Bring down my 3. Well, 7 will go into 33. It will go in 4 times, leaving me with 28. Okay, and that's going to give me a remainder of 5. Well, that doesn't work. Okay, so we can kind of just say, nope, nope, not that one. So how about 11? Well, we know 11 is a prime number. Let's try this out. Let's do 11 divided by 103. Well, when we start trying that, we can see that 11 will go into 103 9 times. Okay, and then when we try that, we can get 99. Subtract that out, and we get 4. That doesn't work as well. And it's worth to point out here, notice that my quotient, which is this right here, is now smaller than my divisor, and so therefore we don't have to worry about anything else. We can go, okay, you know what, I don't have to go on to like 13 and I don't have to go on to 17 because it's not going to work. Only thing that's going to happen is it's just going to get smaller and smaller and smaller. So we're going to find out now that no, 103 is prime. Okay, so 103 is prime. Okay, because we're not finding anything else. So, is 221? Well, how about 221? Is it going to be a prime number? Let's start checking it out. First off, let's go with some divisors that we know about. Is 2 going to work? No, 2's not going to work. How about 3? Well, 2 plus 2 is 4 plus 5. Well, that's not going to work either. Okay, well, how about 5? Well, my 1's position is not a 5. That doesn't work. Okay, so let's just start thinking of some other numbers here. We got to start at 7 now. Okay, let's come in here and let's do 221. Oops, change colors again. Let's do 7 divided by 221. Well, 7 will go into 22 3 times, and that's going to give me 21. Comes down to a 1, and then bring down the other one. This will go in 1 time. Automatically, you can tell I'm going to end up having a remainder here because I'm going to have 7. And so this is going to be a remainder of 4. Okay, well, let's try the next prime number that we know about. We can do 11. Let's do 11 divided by 22. Oh, sorry, 221. And 11 is, well, that's going to go in 2 times here, giving me 22. That's going to be 0. Bring the 1 there, well, that's just going to be a 0 because 11 won't go into 1. Bring down this, and then we get a 1, we get another remainder. So it doesn't work. But notice, this number is still larger than this number here. So we can keep going. Let's try 13. Okay, 13, and then we're going to do the 221 again. Okay, well, 13 will go into 22 1 time. Subtract off the 13. Okay, and we're going to get 9. Bring down the 1. Okay, 13 will go into 91 7 times. Okay, 7 times 13 is 91. Okay, and then notice we get 0. So look, we have 13 and 17. So we know now, because remember, we can double check this and see if this works. I should be able to take this 13 and multiply it by 17 and get back to 221, which means if I can do that, that means that this number has more factors than just 1 in itself, And so therefore 221 is composite. And that's how we would find out numbers are a prime or not. And it works very well for large numbers. Lower numbers, you're just going to start kind of just understanding them through just learning your multiplication process. You're going to start noticing the ones that are prime. Okay, the fundamental theorem of arithmetic. Every composite number has exactly one prime factorization. Okay, here we are. What we're going to do is we're going to factor the composite number into two factors. Factor each factor that is not a prime, and continue this process until all the factors are prime. What does that mean? Well, I have just an example here that they already did for us. Find the prime factorization of 9. Okay, you can think of anything. What will ever equal to 90? Well, 9 times 10 works, just like they use here. Okay, well, let's start thinking of prime numbers. Are there any prime numbers I can think of that are going to create that 9? Well, notice here, 3 times 3, that creates 9. How about 10? 2 times 5. Okay, so notice here is my prime factorization of 90. If I multiply all these back together from here to here, I'm going to get right back to the 90. Okay, we can also start with a different set of factors. Okay, we'll do it on the next page. Look what happens if I start with 3 and 30. Okay, well, 3 times 30 does equal 90. Okay, 3 times 10 is 30, times 2 is still 90. Okay, but notice here, this 10, I can still create 2 times 5, and then this 3 just comes down because it's prime. And so therefore, this is the exact same numbers I got from the previous page. If you look, 3, 3, 2, 5, and here 3, 2, 5, 3, same numbers, just different order, doesn't really matter. Okay, but they still work, and these here would still multiply out to 90. Okay, so notice the final prime factorization was the same in both factor trees. So let's do another one here. Okay, since the multiplication is commutative, the order of the factors is not important. What is important is that all the factors are prime. Writing the factors in ascending order, we can write 90 is 2 times 3 times 3 times 5, or with exponents. You're going to be wanting to do this, get used to doing that a little bit. It's going to help out. Okay, so let's do some prime factorization here. Okay, looking here at 65. Okay, I'm going to write this over here. We'll just kind of make a little tree here for A, and we're going to do 65 right here. Well, looking at it carefully, notice I have a 5 here, so whenever I divide this by 5, I end up getting 5 and then 13. Well, notice 5 times 13 is going to equal 65. Knowing about primes, I know this guy's a prime, and then I can't think of any other multiples for this one, so this one's already done at 5 and 13. So therefore, this is the prime factorization of 65. Okay, let's do the next one. Let's do B. Let's do 72. Okay, 72. Well, I know that 8 times 9. Okay, just thinking of my multiples, 8 times 9 is 72. Well, let's think about this further. Are there any other primes that I can come up with for 8? Okay, well, how would I make 8? Just thinking of just multiples I know quick. Well, how about 4 times 2? Okay, well, notice this guy here is still not a prime, so I can come in here and go 2 times 2. So 2 times 2 is going to be 4. 4 times 2 is 8, and then, okay, so we're good there. Well, how about this side? Well, anything I can think of for 9? Well, automatically we can think of 3 times 3. So the prime factorization of this guy, if you want to kind of look at all the numbers, it would be 2 times 2 times 2 times 3 times 3. It's all the bottom numbers at the very bottom of your tree. Notice I didn't use 4 because I had to branch off from it, but it is all the bottom numbers. So 8 times 8 is 2 times 2 is 4. 4 times 2 is 8. Okay, 8 times 2 is 24, and then 24 times 3 is going to be 72. Okay, and we can go ahead and do one more. Let's do the 294. Oops. Write that correctly here, 294. Well, how do we factorize that? Well, looking at it here, I could go ahead and start adding all this up and saying, okay, well, this is going to be even, so that's going to be divisible by 2. Well, then, can I see if it's divisible by 3? Well, 9 plus 2 is 11, plus 4 is 15. That's divisible by 3, so I also know that this is going to be divisible by 6. When I divide this by 6, I end up getting 6 and 49. Well, what's good about 49 is if you think about it, we can think of two prime numbers right now, is we could think of 7 times 7. So don't get scared seeing these large numbers like this, thinking, oh, it's going to take a lot. No, that's how come we did the divisibility test before. See what it's divisible by, and then start dividing from there, and then you can start prime factorization the smaller numbers. Remember, because it doesn't matter what factors you use, they're going to factor out to the same. So notice on this one, the factorization here is going to be 6 times 7 times 7. So 6 times 7 is 42, times 7 is going to be 294. All right, let's continue on. Factors of a composite number. The only factors or derivatives of a composite number are 1 and the number itself, okay, we learned that, each prime factor, okay, and products formed by all the combinations of the prime factors, including repeated factors. This one I just kind of kept as their example, just so I can kind of show you. Okay, let's look at this one. Find all the factors of 60. Come in here, change colors here. Notice, the prime factorization of 60 is this. If I had to write it over here, you kind of see it a little bit better. Okay, it's going to be 2 times 2 times 3 times 5. This is where they're getting that 2 squared from. Thus, the factors are 1 and 60. We know that because 1 times 60. So here's this, 1 and 60. Okay, each prime factor of 2, 3, and 5. Okay, well here's the 2, the 3, and the 5. So here we are, 2, 3, and 5. Okay, and then products of all the combinations of the prime factors. So notice what's happening here is they're starting with the 2. Okay, so we start with this 2 here, and then we're going to multiply this 2 to here, to here, to here, and that's exactly what they do. They go 2 times 2, okay, and then 2 times 3, and then 2 times 5, okay, and then they do the 3, and 3 times 5, which is what's happening right here, okay. Then they're going to come back and do the 2 times 2, so we go 2 times 2 times 3, 2 times 2 times 5. And then we can just take this final one and go 2, 3, and 5. They're literally looking for every little combination, which can get a little bit daunting, but you can kind of see something in here, because notice in 15, well, 15 times 2. Okay, well, what's the prime factorization of 15? It's 55 and 3. This is going to be one of those that just after time, you're going to get really, really good at, okay? But these are all the factors of 60. These are all the things, every single thing you could be able to divide out, and you would get 0, okay, remainder. So that's how that works.